Hi. In the previous part of our lecture, we discussed about hypothesis testing about our population parameter, which is our population mean, when we know this population standard deviation. Now, as is mostly the case, or what is the most common scenario, is that we do not know the population standard deviation, especially true if it's a research for scientific research or in the research that we are doing. So, if we do not know the population standard deviation, there are three possible cases that we have. So, case one has the three conditions. The first is that the population standard deviation, sigma, is not known. You have a small sample size, but the population from which the sample is selected is normally distributed. Case 2. So for case 2, we also have unknown population standard deviation, but we have a large sample size. And in this case, the rule of thumb for a large sample size again is greater than or equal to 30 samples, or the number of respondents in the sample is greater, or elements is greater than or equal to 30. And the last case is you have unknown population standard deviation. You have a small sample size of less than 30, and we do not know, or we the shape of the distribution is not normal. So that's case number 3. So for the approaches, so for case 1 and case 2, both of them, since you have either a large sample population, or if it's a small population if it's a large sample size, or if it's a small sample size, but a normal distribution, a population is normally distributed, we use here the T distribution test. Now, if we can draw the parallel with the previous, from the previous lectures, if we know the sigma, if we know the population standard deviation, we were using the normal distribution curve, which is using the z values. Now, for unknown population standard deviation, we are not using the z curve, but rather we are using the t distribution. So take note of that difference here. If we do not, we know the sigma, we know the population standard deviation, we use the z value, the z table, because you are using the normal distribution curve. But for unknown population standard deviation, we are not using the normal distribution. Instead, we are using the t distribution. And then for case 3, small population size and not normal population distribution, we are going to use non-parametric methods. But we will not be covering that here. So like the z distribution, we also have your test statistic t. So very similar approach on how we do that. So test statistic t for the sample mean x bar, it is computed as the sample mean minus the assumed population means over your SX, which is your normalized sample standard deviation. S is the sample standard deviation, and this is the S sub x bar is the normalized sample standard deviation, because you divide it by the square root of n. So the value of t calculated for our sample mean by using the formula is the observed value of t. So this t value is the observed value of t. So let's have this example. So a psychologist claims that the mean age at which children start walking is 12.5 months. So Carol wanted to check if this claim is true. She took a random sample of 18 children and found that the mean age at which these children started walking was 12.9 months, and with a standard deviation of 0.80 months. So this is the standard deviation for the sample. So it is known that the ages at which all children start walking are approximately normally distributed. So the p-value for the test, find the p-value for the test that the mean age at which all children start walking is different from 12.5 months. What's your conclusion be if the significance level is 1%? Now from the question itself, the approach that they are asking us to use is the p-value approach. So similar to how we do the hypothesis testing if we know the sigma. So we first describe or state our null and alternative hypotheses. So we have, for the null hypothesis, mu is equal to 12.5. So there's no significant difference. So the average here is 12.5 months. Oh, sorry, the average month for walking is 12.5 months. The alternative is it's not 12.5. Since it's not equal to is our alternative hypothesis, we have a two-tailed test. Now, step 2, what type of distribution is this? The population standard deviation is not known. We have a small sample size, but it's a normal distribution. So we're going to use the t-table or the t-distribution table to find the p-value. So step 3, since we are going to identify its single-tailed or two-tailed, so the sign is not equal to. Therefore, our test is two-tailed. So our test statistic is 2.12. So that's our t value or our observed value of t. So that's t is equal to 2.12. And for we have the p-value, our p-value is calculated using our t-value or t-statistic. So here's our t-value. We have from our t-table the degree of freedom, how many elements, or what is our n? Our n is 18. We have 18 respondents or 18 elements in our sample. So degree of freedom is n minus 1. So 18 minus 1 is 17. So from our test statistics, so the p-value is between 0.02 and 0.05. This is from the table. So here is the p-value. So this is our t test statistic, which is obtained from our sample mean. This is negative 2.12. So this is a two-tailed test. So that means the value of p is divided between the two sides. So find the area here plus the area here. So that's the total p-value. So for any alpha greater than 0.05, so the p-value here that we have is between the value of 0.05 and 0.02. So for any alpha greater than 0.05, we have to reject the null hypothesis. But for any alpha less than 0.02, we will not reject the null hypothesis. So for this example, since this is based on the table that our p-value lies between 0.02 and 0.05. Because again, the table is a bit constrained. We are a bit constrained with the value here. So our example alpha is 0.01, which is less than the lower limit of the p-value range of 0.02. So 0.01 is our alpha. Our p-value is greater than our alpha. So therefore, since it's greater than our alpha, we reject, or rather we do not reject the null hypothesis. We have a high p-value. So if it's higher than our alpha, we do not reject our null hypothesis, and therefore we can conclude that the mean age at which all children start walking is not significantly different from 12.5 months. So here, just remember, we only reject a p-value if the p-value is smaller than our alpha. And since based on the table of t-values or t-statistics, the p-value lies somewhere between 0.02 and 0.05. So, and our significance level is 0.01. So, 0.01 is less than our p-value. So, p-value is greater. So, as long as the p-value is greater than our alpha, we do not reject our null hypothesis. So, if we say, for example, if we change our alpha to say 0.05, that is the time we will reject the null hypothesis. And actually, that's one of the reasons why some researchers prefer to calculate the p-value instead of using the critical statistic or the critical value approach, because this is more versatile. We can change the alpha significance level without really changing much, without really recalculating everything else. So again, for example, we know the p-value. It doesn't change. The p-value is dependent on our sample statistic and our, of course, degree of freedom. Therefore, it's a consistent value as long as our sample doesn't change. We can change our alpha, our significance level. We can make it a higher significance level or a lower significance level. But we do not change the p-value. That's why p-value approach is much preferred for researchers because, again, it's versatile. It can be used without we don't have to recalculate anything. We just need to compare the p-value and our significance level in case we want to change our significance level. So anyway, as long as our p-value is greater than the significance level, we will not reject the null hypothesis. So let's have another example. The Grand Auto Corporation produces two auto batteries. So the company claims that its top-of-the-line never-die batteries are good on an average for at least 65 months. Ang a consumer protection agency tested 45 such batteries to check this claim. It is found that the mean life of these 45 batteries to be 63.4 months with a standard deviation of 3 months. So find the p-value for the test that mean life of all such batteries is less than 65 months. So what will be your conclusion if the significance level is 2.5%? So again, this is less than 65 months, so we are looking here at a single-tailed test. So let's have our applications. So step 1, state our null and alternative hypothesis. So since the claim here is at least 65 months, the average lifetime of your battery is good for at least 65 months. So the average lifetime is greater than or equal to 65. So at least 65. And our alternative is less than 65. So we have here a left-tailed test. Step 2, what type of test are we going to use? So we have here unknown population standard deviation. We do not know sigma. But we have a large population size. So we can use, this is case 2, so we can use the t-distribution. So the sign of your alternative hypothesis indicate that you have a left-tailed test. And so find our t-statistic and our t-statistic from our sample mean. So just plug it in the equation. So x bar, that is a sample mean from our sample of 45 tested batteries. We have 63.4 months on average life. So 63.4. And our population, sample standard deviation from the data of the 45 batteries is 3 months, plus minus 3 months. So you have the normalized standard deviation. And so you have a t-value of negative 3.758. And the degree of freedom is 45 minus 1 or 44. So from our t-statistic or the t-value table, our p-value falls around or less than 0.001. It's actually very, very small. So here is our p-value in our t-statistics. We are looking for an alpha value of significance level of 2.5. So that's an alpha value of 0.025. So basically, since our p-value is very, very small, we therefore reject the null hypothesis. And so the claim of the Grand Auto Corporation that at least 65 months is basically not true because we reject the null hypothesis and accept the alternative. Alternative is that the actual mean is actually less than 65. So this is our p-value is very, very small. So as long as we have a small p-value and it's smaller than our alpha, which is 0.025, we have to reject our null hypothesis. So that's it for the p-value approach for a t-statistic distribution.